That's okay.
Hello.
Because I have 10.
Web, right?
And
Now
that
we
takes
did
some
last year.
Thanks.
How much does it cost?
Yes. Está bien.
Five, four. Not by three. Yeah, at least five.
Okay. Hurry up. Settle down. Hi. Hi, we're going to start the lecture. Hello. Hello. Okay, are you ready? Okay, we'll start a lecture today. So welcome back. This is the second half of your semester one, and we are going into the digital part of the exercises. Okay, so just a quick recap on what you have done for the first part, the analog part. I think we have gone through exercise one, primitives. We have learned about solid void, crochet, figure ground, some simple platonic geometry, symmetry, center axis, subtraction, and extrusion. Okay, so we are now familiar with some of these precedents. We look at some of these drawings, these buildings, platonic solids, and then you build model based on platonic geometry, very simple cylinder, cone, and things like that, right? Okay, so this is the first part, first language of how architecture is built. You have some basic geometry, and then you do an extrusion to become 3D, right? So you have something on plan, and then you kind of extrude. So this is the way it's done, right? The second exercise, Cartesian, you have gone through some grids, point-slice planes, and then asymmetry, and it's a language of addition. So you have addition of all these different elements. You learn about probably 4-square grid and 9-square grid, one with a solid in the center and the other one with a void, and they conceptualize a lot of these grids. Right, you learn about domino house where the buildings are stacked, and this is the grids organizes structural part of the building, and you have all the curves and elements that's off the grid that is providing you the spatial experience of the building, right? So it's a gridded building, but you never experience the sort of grid because the infill walls and things like that throws you off the grid, and it moves you. If you study hub house, it is off the grid in Y direction and then in X direction, and it also starts to generate this kind of pinwheel movement, right? Rotational and diagonal movement in otherwise stable architecture. Okay, so we have second one, Cartesian. So you may have different spatial experience for every floor, and you stack all the floor. So this is how 2Ds become 3D. Okay, so for exercise 3, we are going to some complex form geometry. I don't know whether you know this building. So in around the year 2000, this building by Frank Gehry was built. Or if you look at this building by Gehry Hadid, that's also built around the same time. This forms the first part of the digital revolution, so-called. So you have previously all the rigid materials you built with foam in your exercise 1, and then second exercise you built with planar materials and sticks, right? So in exercise 3, you're going to learn some malleable materials like fabric or clay or paper, right? So Gehry did all this model, and then basically the idea is that how do we? So he made all this, right? So this is not a cube. This is not a sphere. This is not a cone, but it's an irregular shape and it's random, right? So how do we geometrically describe this building or get this built? Okay, so if you look at you can listen to this talk. It's in the reference list. Second digital turn by Mario Capo. He describes this as a potato, right? So potato is a odd shaped geometry. It's not a sphere, it's not an arc. You cannot find the center, and it's very complex, right? So how do we geometrically describe this thing, right? So any irregular form, we will call it a potato, right? So one of the exercises that I got my students to do over the break is that you cut the potato into slices, right? So you have a lot of sections, right? So with with a classical building or a primitive building, you probably only need one section or two sections, and you can describe the whole entire building, right? So with a potato, you need multiple sections, right? And all these sections, the more sections you have, the closer you'll be to the shape, the complex geometry. Okay? So, and then once you have all these sections, so what they do? So this is a bit like CT scan, right? So this is a CT scan of the foot where you cut many slices, right? Your foot is also something very complex. So this is, so in Rhino, I hope we have learned over the break, there's a complex shape, and then you can have X number of sections, right? And then on each of the section, you can have a certain number of points. And when you join these points to the next point, point one to point one, and you will get a rather complex form. Okay, so this is the easiest way or the simplest way to describe a complex form, of course. And you may also get a few critical section, right? The largest and then the smallest, and then you can input it into the computer and generate all the in-between sections. Okay, so these are some of the diagrams that shows you whether you have the green one below. You can see that the green sections are not at regular interval, but with the software you can easily rebuild and get regular sections for your construction of your model. Okay, so this all starts because Frank Gehry was trying to build this sculpture. It wasn't even a building, right? So like, how do we go beyond orthogonal Cartesian geometry? So he was trying to build this fish. As you can see, is an irregular shaped fish. And then he actually borrowed a software, a computer software, CATIA, from the car making industry. Okay, and then you will have all this curve describing the shape, but this forms the surface of the shape. Okay, eventually you can see that there's regular sections cut, and this forms the structure of the fish. Does it make sense? So it's always structural, right? Your buildings have to stand. So in a way, this is confined by conventional building techniques like steel and concrete, right? So you have all these structural elements inside and the skin, okay? The facade and the skin. Okay, so these are some of the building model. As you can see, behind the smooth facade, you have all these regular, there's a lot of structure holding up the skin, okay? So this is some structure under construction. The inside, sometimes you can see the facade of the structure. And then hive, right? Hive, you're going to visit maybe today, maybe on Thursday, but you can see the whole design process. Like it started with some clay, right? So a malleable kind of material, it's not rigid. And then slowly it builds the massing and then the spatial model where it shows floor by floor by floor, right? So every floor in a way differs. So in Cartesian, it's probably kind of repeated in a way, and then this is differing. Okay, so sometimes you can also express the slices, not in terms of structure, but the form itself is stacked by all these slices, right? Okay, and then so the second part of the building basically is about the skin, right? So how after you have all these slices that builds the structure of the building, you can learn how to compose the surface. Okay, so there are a few ways. You have NURBS, mesh, and sub-D, different ways where you can start to make a smooth surface, right? So it's no longer something very straight, but it's a kind of surface, right? So from this one, so you can see that it starts to think about how they want to make the surface. It starts to have this is it's a diamond kind of geometry, right? Or in this case, they're like strips, right? So how do you actually model piece by piece by piece? So the same surface, you can have different ways of describing. So this is the final built one where it's more rectangular, but every piece is actually different. Okay, so it's no longer always the same. Right? So in this case, then it's all trapezoidal. Okay, you can you can experiment, right? It depends on what is the concept or what kind of feeling you want to express for your surface. You can play with different scale, different sort of geometry for the surface, right? So the potato can also be described in this kind of Voronoi cells, if you want, not just in slices, right? So in exercise 3, you can learn how to build the same complex form that you created in different ways. It depends on what you want to convey, right? Do you want to express the slices or do you want to express the surface? And why do you choose this geometry over the square or rectangular shape? Okay, so this is the same shape described in slices, a smooth surface, and a discrete kind of surface. Okay, so you learn how to construct all this geometry. And you can see that's the skin of the fish. All right. So one thing I want to talk about. So in the beginning of uh, this evolution, I think if you look at the sections and the plans of the building, in this building, what do you recognize? So a lot of the parametric part is actually applied only to the skin, right? Do you recognize the inside of the building? Is there a diagram from Cartesian that is very close to this? Domino house, right? So a lot of, in the beginning of this digital revolution, I think a lot of the parametric thinking is applied to the skin, but spatially it's still a rather Cartesian building, right? So it's something that you actually look at that looks like parametric, but if you walk through this building, it's pretty much this or less exciting than a Cartesian building because it's just a grid. There's no offset elements in the Cartesian building. Does it make sense? Right? But this is the beginning part. So so we have this and we don't have the infill elements in a lot of this building. And I think when Gehry did, he's also more intuitive when he created all this complex form, is maybe sculpting it with paper, right? So in this exercise 3, I think one thing we try to do, I don't know, is to, I think different studio will have different methods of generating a rather complex form. Okay, so you can experiment with materials. Okay, so any materials that you like to make a complex form. Okay, so you push the limit of clay, I don't know, wax or bubbles or whatever you want. Okay, so try to create something that is not primitive, that's not Cartesian. That's one way. And then another way that I can think of is actually thinking about mapping a body in space. Okay, so this is horse and this is like dancing, right? So as you map all this movement, is to get some sort of mapping. At least you learn the mapping technique. At least it's not something like I just crush the paper and say I like, right? So there's some sort of thinking in this. So whatever you want to map, and then if you map the horses or the dancer, you which points on the body you choose to map is related to the movement that you are mapping. So it doesn't have to be your body, it can be a cat, it can be some object in space, right? The leaf falling. Okay, so then which points on the leaf you choose to map, so you kind of get a rather complex shape that you cannot imagine. Okay, so I think I'll leave it to each individual studio to think of how they want to generate the complex geometry. Okay, and then the exercise that you are, the techniques that you're trying to learn is that the design process is actually a smooth process, right? So you play a dough and things like that. But eventually, when you build with our current traditional building techniques, you will have to change this material into a discrete components. Does it make sense? It means you can't actually, let's say this is a dough, right? This dough. The dough is not the material that is used to build this shape eventually. Eventually, it's turned into metal or steel or plywood, something like that, right? So that conversion is what you are learning. And of course, this is really now the technique has gone beyond this, right? But we can simply start with this first. Okay, so you have a rather dynamic kind of design process, and then you learn how to change it and describe it into rigid materials, components of rigid materials. Okay, so this is a work from last year. I think he used some soy and glue kind of mixture. Then he invented a little device with all the bamboo to measure the sections, to take the profile of all this thing and then translate it into a digital model. Okay, so the point is not to use a 3D scanner. Of course, you can put inside a 3D scanner, but the point is that you understand the thinking of how to describe a complex geometry. Okay, that how you can generate something complex from just a few sections and you can loft it. Understand? Okay, so if you just do everything 3D scanner, and what if you have no 3D scanner? So this is not a new technique, but in the past, I think when you build a ship, a boat, right? So that's when it's also quite complex, right? So people actually build sections by sections by sections. Okay, so it's nothing new. It's just a computer can do much faster, but much more refined than you, right? Maybe by hand you only cut 10 sections, but the computer can give you different options of section interval in just split seconds. Okay, so understand the thinking part of this technique first. Okay, so this is some of the past year students' work, what they have built. I think there's a mapping of someone moving, and then she built this model. Okay, so whichever these are the slices, and then I think that's the easiest one to start building. You don't have to think, like just build the mess out. Then you start thinking whether you want to express the slices or you want to express the skin, right? And what are the intervals? And this depends on what you're trying to convey. Maybe you're trying to convey something smooth, right? Then you think about how to build the surfaces smoothly, right? What is the scale that you want, right? But if you want to express steps, right? Then I would choose certain other building material. Okay, so these are different models that you can build. Okay, so that is exercise 3. So I'll quickly go through exercise 4 as well so that you have a better overview when you go inside. Okay, so this exercise 4 is actually about building a family of potato. It's a series, it's a series of forms that is related by an algorithm. Okay, so for example, okay, in nature, you have trees, right? So all the trees they look different. If you measure, it's slightly different. But you can recognize that they are the same species, right? Because they share maybe the same number of um, branches or the branching method, right? It's like one branch into three, something like that. Okay. So for example, we are all human. We all look different, but we always will have two eyes, one nose, and one mouth. Okay, and the number of bones are the same, but the length of the bones may be different, right? So in this series, maybe your external property, which is uh, length, area, volume, something that traditionally define architecture is no longer important because it becomes a range, right? So like the tree. So let's talk about the height of the tree, right? Or the size of the tree. Every tree is different, but you understand that they all belong to the same species. Does it make sense? So the intrinsic kind of algorithm is more important for growing this kind of form, a series of form. Okay? So traditionally, I mean conventionally, topology is defined by this, right? Like they will say the donut and the cup, they belong to the same algorithm or topology because both of them have just one hole, right? So if you morph and mold the donut, eventually it will become a cup. Okay? So here you will learn there's a lot of already you have gone through your some basic grasshopper learning. I don't know, right? So these are some of the like Voronoi, which is points, and then you get the middle line of the points, and then you form this kind of shape, right? So there are some mathematical, very basic mathematical series that you can create with the basic preset tools in a way, right? So you have a field, vector field, and all these kind of things. Okay, so uh, okay, so it's a bit like in the 1968. I think this artist so Louis, he basically didn't. He stopped painting something, but then he gives a set of instruction, right, and then you will generate the artwork, right? So he did uh, sculpture in this manner as well, three sides. Then if you have four sides of the cube, then you get all these variations of sculpture. Okay, so the potato, this is from last year's student. I think some of the students tried to grow a series of form using the basic tools in Grasshopper. Like they will vary a series of Voronoi points and then you get different potato shape. Okay, this is one way. This is something for them to learn Grasshopper. It's not really uh, predictable. So this is another guy. I think he starts to describe the potato shape as random points in the section. So you randomize the points and then you get this a series of this kind of different shapes of potato. Right? So this is another relation that is trying to link or create a whole family of potato. It can be anything, right? But it's this thinking that we're trying to engage here. So in terms of space, just now you saw that the Zaha example, right? Where the parametric is applied to the envelope and then the inside is just the Cartesian one. So in Japan, starting around 2000, you have with this project by Toyo Ito, he starts to think about how he can morph this diagram, which has been around for about 100 years, right? So he basically did change the columns into all these individual columns, big and small. Then some of them are occupiable, so that and then the columns are also not strictly falling on the grid. They are a bit off grid, right? So that you can imagine the spatial experience is more uh, fluid than the Pilates. Okay. So with that, and then SANAA, I think, went on to create a series of this kind of museums and buildings. So you start to have within a building a range of spatial quality, right? A range of different, there are boxes, but in a way they are spatially parametric, not form. Okay, so parametric thinking can be applied to the envelope, which is the form, the solid part. But here we have very simple geometry, but very complex spaces. As you go from no two boxes are the same, right? Uh, they did Moriyama house as well, based on the same idea. So you can, Cartesian is in a mass production 1900 kind of era. So you always repeat things in a way. But here they are almost going for a range, a spectrum of diversity, right? So in a building, you don't always have your four bedrooms. Your bedrooms always look the same, but they're trying to create a range of environment like you walk in the forest. Okay? So you get another Ito's museum where you have rules and then how the corners are bent, folded, and then you get a series of this kind of forms there. Okay? So the Japanese are trying to, they always want to demolish the boundary between built environment and natural environment, right? So they call their architecture landscape light architecture, all right? So then you have Kite, something that's built in by Ishigami in 2008, right? So this building has how many columns? I can't remember. Like a lot of columns, but no two columns are the same. Okay, so this is the list of all the columns in different direction and width, right? So he's trying to create, and then you can see that you no longer can draw the boundary of the room, right? Not like classical building, you can like, oh, this is circle, this is a room, and then it's enclosed, and then Cartesian, a bit less, you can still, the corners are demolished, and then, but you can still kind of get the shape, right? But here is really like a forest where you choose where you want to inhabit, right? So if you feel like today you want to camp there or you want to work there, you can, right? So there's no fixed path, and it's this kind of openness of architecture. All right. Well, sometimes, to be honest, I think he did this by hand, right? By adjusting everything, but I think you can easily write an algorithm or something to scatter the columns, okay? But he did it by hand, which is, so the tool actually is not, so it doesn't mean that you 3D print something, it is parametric, right? If you 3D print a box, it's still a box, okay? It doesn't, the architecture is still a box, right? So if you, but you can also do parametric by hand. It's the thinking that's more important, right? That you think about this, just that maybe with the technology it's faster, right? So sometimes it talks about the thing being like birds, sometimes galaxy or trees, right? So it doesn't matter. But from the outside, when you look at this building, this is how it looks like, okay? So compared to just now the Azerbaijan Museum, you can see that in the beginning, parametricism is applied to the envelope and you have something inside that is very close to the window house, right? So it's something, it's a form where you are outside of the building and you look at the building and say, oh, that looks parametric, right? But the Japanese are probably trying to do this. They have very complex structure, space. So a lot of this parametricism hits the structure, but the envelope is just like a cutoff point. Okay. So if you go back to this building, you probably won't spend a lot of time looking at the building from outside, but you can spend a lot of time wandering around on the inside. And it will always change with the weather, light, and shadow. Okay, so there's a key, there's no right or wrong, but it's just an analysis of how we can use this new tool, right? Okay, if you are interested, you can read some of the philosophical change in uh started by the news, and then they basically talking about again something that is non-hierarchical. So traditionally, architecture is also very hierarchical. There's always the main spaces and then the corridor, right? And then there's a less important spaces. But then I think in this new series, I think they are trying to make some very flat spaces, right? So the corridor is as important as the spaces itself. And in fact, maybe there's no more corridors. Okay, so there's, you can read not so, but it's a change in philosophy thinking, right? How we look at the world, the view. Okay, so like if you want, traditionally you have banking system, you have government, which are very hierarchical, so economical system, political system, right? To something that is very flat. So you have your crypto, you have your versus the traditional banking hierarchy, right? And then you have the government that controls top down versus self-governing. Okay, so these are systematic changes in architecture that you guys need to deal with. Okay, you can no longer build boxes because it's been done, it's over. Okay, so for exercise 4, how do we do this? So one of the ways is uh how to say, I think the point is also not to start from the software. Okay, so we start from the thinking. You can understand a few presets tools, right, that you have. But the whole point is that you maybe start from a dynamic model that gets you out. So you start with your hands, your analog model. So when you simulate all these dynamic relations, you may need to combine a few of the tools that you have. Okay, if not, because everybody who use Voronoi, then your form will look like Voronoi. You can never break away from that kind of form. Okay, so one of the way, then we went back. I went back to look at Gaudi. if you know Gaudi, right? Spanish architect, right? So this is the building that's still under construction. 1800, I think. So since 1800, it's still under construction now. He cannot calculate forms like that. Okay, basically they don't have computer, but how they got this built is by doing an upside down model. So this is a model of chains and weights. Okay, so if you have a chain and weight doing this, you can kind of freeze it, invert it, and it becomes your arches. Okay, so he did the calculation by hand. I mean, like by building model, right? So model is the closest thing that we have to our real building. We can never mock up one building and then build the second one, right? So how do you know? So you build models, and if the models are bigger, then they are closer to the real building. The lighting condition as well, the structural property as well. Okay, so he did in 1800 already a parametric building. Okay. Then you can look at, if you go to Barcelona now, I think you can still look at some of these models. So there's a mirror at the base, so you can see now the building right side up. Okay, does it make sense? Okay, so you have another architect in the 1970s, is it 50s? Frei Otto, right? So he also uses a lot of chains to study odd shape curvature, right? So if you have a dome and it's a perfect hemisphere or kind of stable circle, it's easy to work out. Okay, but you can see this is a upside down model of a continuous surface, right? With different arches, right? So he's trying to build an upside down model so that he understands where to have all the support and columns. Okay, then he uses a lot of this bubble film, right, to find form as well. So he's using material to find certain form before the computer arrives. Okay, so this is bubble, right? And then so by designing all the different wires, you can have the bubble find the thinner surface that covers all this odd form, right? So it tries to. So of course, these are some of them, this bubble tensile material. I think you can now easily just simulate in computer if you want to, right? But just to say that, how to say, like without the computer, you can use material or model to help you create forms, right? That's beyond primitives and Cartesian. All right, so you can go read this book. Probably he documents a lot of his experiments. Yeah, it's quite fun, right? So some of them is like he studies dispersion of all these things, right? Can we not have grids? Can we think about density and dispersions, right? The same bubble, but different structure. Just how the bubble was to find all these big surfaces. Now you have all these different clustering and how he controls the size of the bubbles, right? So this is Voronoi geometry. Then he's trying to study all this. So, but now you can just build it very quickly. Okay. So with those basic, oh yeah, this is a density of bubbles if you want, density of different bubbles. Okay. So then, yeah. So for exercise 4, these are projects from past year. I think I don't know, maybe each studio will also have their own different approaches, but I try to start with a dynamic kind of model. So this model is like sand falling through obstacle, and then you can vary the size of the sand or the size of the obstacle, and you try to study things. Why? The point is that then we try to use this as a muse for us to combine, to describe different relations. Okay, let me show you the next one. Okay, like this guy, he did it's a speaker at the bottom, and then there's all this foam ball, right? So when you on the sound, and then all this foam ball kind of bounces, right? So how can we model this? So we are not trying to simulate this thing physically, but one of the ways, so is it, okay, how about I describe the Brownian motion, right? So it's erratic kind of material, and then it's affected by the sound, and it's also affected by the number of the balls. Okay, so this is one relations that he can describe out of it. And then he said the second relation is, okay, how about I model the balls and they have connections between all these balls, right? And the balls, I can change how springy the spring is, right? So if it's more rigid, then when the ball scatter, it's not going to scatter too much. It will keep to its shape, right? But the top one, because the spring is looser, so you get a kind of bigger dispersion, right? And then another one, then you say, okay, how about I just have one ball, but I change the shape of this different ball and then see whether it affects the trajectory of the ball. Okay, so this is to try to so you don't start with the presets, right? If you probably a combination of preset, and then you got to think about what is the outcome, the form that you want. Okay. Then maybe some analysis of why, because you have endless iterations. So you can think of some analysis of why certain iterations are better than, right? So you will have to perform a kind of selection process. Why? What is the criteria? Is it structure? Is it that it's bigger? Is it, what is it? Okay, so you can exercise. It depends on your concept, right? How you want to select the form, right? Why is this one better than that? Okay, and then after that you can print. You can use 3D print and print one of the selected forms. Okay, so you will get some of the forms that you print, whatever you want. Okay, so I so this is another project. I think they drop some straw and string inside water. So, also trying to think of how to model this, maybe describing the rigid part at some points, and then there's the loose part, and then how this form kind of expands and contracts, right? Okay. So you grow, you start to grow. So in exercise 4, you have a series of forms, okay, that's connected by a sort of mathematical relations. Okay, and you learn how to calibrate all these relations. Whereas exercise 3 is about one fixed, complex sculptural form that you then try to build, right? So there's a smoother design process, more elastic, and then you freeze it and you try to convert it into something rigid. Okay? Okay, that's all. Any questions? Any questions? Questions? Good? All good? Clear? Okay, let's go.